All right, there we go. We are recording. We are going to go over into the lab. You all are going to sit on the far side of the lab. When we leave the lab, all of the stools are going to get put back up on top of the counter. There's also some paper that has fallen on the floor. If you could help me out when we leave today, making sure that some of that extra stuff gets picked up and cleaned up, that would be great. I'm going to go over there first with the camera so I can get it situated. And then you guys are going to come in. Please make sure you watch out for extension cords. Do not trip over them. I'll do the best to try to get them pushed to one side of the door so that then you just have to step over them once. You do not need your lab notebook this time, but you definitely need the lab paper with you. So bring a writing utensil and also bring your lab paper with you. Let me get situated before you guys come following. I want to make sure I get all the cords and everything out of the way so we're not tripping over them.
Hey, Mr. Windsor.
I could hear you for a second there, Eric, and then you kind of disappeared.
Is the FaceTime button, can that be used, or no, since you have a Google Meet going?
You can try the FaceTime button. I mean, the worst comes to worst, you have to jump on it again. All right, I have everything situated. We're gonna head into the lab and get ourselves where you.
About ready.
Please make sure you situate yourself in a place where you have the ability to write and also where you can see. All right. All right, we are about ready to perform our lab. What observations can we make right now based on what we see? What can we state right now about this tank and its setup? Yes, ma'am.
There's a heated lamp.
There is a heated lamp. Mr. Reg, don't touch the lamp, but if you put your hand close, what do you feel? You can feel it's hot from there, right?
Yeah.
It's pretty warm. And so if I put my hand right up close to this, it's hotter and hotter and hotter. And obviously I don't want to touch this because this is probably really hot. All right. I want to make sure that the Van Kuykens and everyone can see this demonstration and that it's recording. All right, I got to move the camera back just a little bit because I'm standing higher and it's like aiming up.
Why are they away from the lounge? So it doesn't fall over.
Yes.
You wrestle too?
Looks like he's tilting a little bit.
Oh, does she wrestle with them?
Not really.
You
can't see it.
Wrestling's a tough sport. Were you wrestling with them too? Always.
All right, I'm going to talk from this general direction over here, and I'm hoping that the camera will situate itself so that you guys can see the demonstration. Could I hear from those of you that are online? Can you see the tank? Is the camera readjusted towards the tank?
It's like halfway on.
Do I need to go towards the lamp side or do I need to go towards the side where the lamp is not at?
The side where the lamp is not at.
So if I move over here and I start talking, is this a little bit better?
Yeah.
Okay, fabulous. So we've got one side of the tank being heated by a heat lamp. We've got a second side of the tank where it is not being heated. All right? And we're going to put some blue dye inside of the side where there is not heat, and we're going to put a little bit of red dye in the side where there is heat. Okay? And we're going to observe what happens. I think, though, what I should do is maybe add a little bit of ice just to help us to represent the fact that this is the polar region. So there we go. We got some ice in there to represent that it is the polar region. And I'm going to put a little blue dye on top of the ice. And I'm going to put a couple drops of red dye over on this side. All right. And we're going to just continue to observe. I'm going to make sure I pull out any partitions that I have. And so now our experiment has started. Right now is about 5 seconds into the experiment. Those of you that are online, can you see the colors fairly well right now? Or would it be better if I shut some lights off?
You can put some lights off. We can't see the red.
Is that better?
The camera's not focused on it now.
Did it start to pick up the tank again?
No, it's focused on Jacob.
Blame it on me.
All right, can you see the top of the screen where the long bar of the camera is? Can you see the tank in that long bar? Or is it still just focused in the wrong direction?
Well, we can see the tank now, but this is the blur color.
Okay, it's just a blur of color. Okay, so we maybe need somebody to explain what observations we are going to add into the bottom part on page 54 where it says, describe what happened. Was your hypothesis correct? What observations can we make now? All right, Ms. Leah, what observations did you make? What did you just see? Or what are you seeing might be a question to ask as well.
That the polar region is sinking and then the tropical region is floating.
Okay, she said the polar region is sinking, or the blue color sunk to the bottom from the polar region, and the red dye from the tropical region is remaining on top. Okay, what other observations can we state? Yes, ma'am?
The tropical region kind of stays together more than the polar region.
Okay, tropical region kind of stayed together more than the polar region. Yes?
The polar region spread out faster than the tropical region.
Interesting. The polar region spread across the bottom of the tank much faster than what the polar region did, where the red didn't move as fast across the top as what the blue moved across the bottom.
So which one's which again?
Red is tropical, blue is polar. Please document whether your hypothesis was correct. Do you accept or do you reject your hypothesis? You created a hypothesis earlier where we wrote down some if-then statements. Do you accept those hypotheses or do you reject them? Mr. Jake.
Is that red stuff on the bottom the light or the dye?
The light.
Yeah, just a reflection of the light.
Yeah, just a reflection of the light. It's that's a good question. So what Jake's looking at is down here at the very bottom. It seems to be reflecting some red light, and so he's wanting to know: is that did some of the dye sink down, or is it just the light coming through causing it to
It
reflect
looks more
red?
orange, which is what.
Yeah, it's definitely reflecting a little bit. Or we might be able to make the argument that the light is being refracted, right? Because as that light's going through the water, it might be bending slightly. And maybe that has something to do with why we're observing it to be slightly orange and not so much red. Kind of like when we put a straw inside of a glass of water. It looks like the straw is not in the same place when it's in the water. Or we put our hand behind that beaker of water. We notice that it maybe looked bigger or smaller. The actual object was slightly distorted because of the fact that light is bent or changes directions as it moves through water. All right, let's flip over to the next page. Number 1 at the top of page 55 says, what is the cause of the movements of fluids? Why did what we just observed happen? What's that?
Heat rises.
I agree, heat definitely rises. What is the driving force of this idea that heat rises? Ooh, density differences. Let's talk about these density differences. What's going on with that heat lamp? What is it giving to the water?
Energy.
Giving energy. What do the particles do right up here where that heat is hitting the surface of the water? Oh, those particles are moving. They're gaining energy. And if those particles are moving and have more movement than the particles that are over here, what is happening to those particles' density? Particles are moving really fast because they're getting more and more energy. Are those particles closer together or farther apart because they have more energy? Farther apart. They're spreading out. So are there a lot of particles in an area, or are there now less particles in an area because they're spreading out? Less. What happens to the density if there's less particles in an area? It's less, lower, right? Density decreases because there's less particles in a given area. So our density is lower over here where it's being heated. Over here, the particles have less energy. They're closer together. If there are more particles in a given space over here, what is their density? Higher or lower? I heard higher and lower. Let's think about it. Particles over here, less energy. They're closer together, meaning that there's more of them in a given area. What's the density? Higher. Does that help to explain why this water over here sunk down?
Yeah.
Yeah, because now we have a higher density. If there's a higher density, the water sinks. And it's going to start making its way all the way over to this side of the tank. What do you suppose is going to happen when this water makes its way over to this side of the tank? Oh, it's going to warm up. Tim, take your hand and put your hand right here. What do you notice?
Warm.
It's warm. Bring your hand over here. Put your hand on this side.
Cold.
Oh, it's colder. So that means these particles are starting to get more energy. What happens to these particles as they get more energy? They move faster. What happens to their density?
They get
It gets lower. So those particles start coming up. They start pushing across over here. They're floating until they come over here and they start losing energy. And as they lose energy, they sink down. And that process is going to happen over and over and over again. This is called convection. It is the movement of matter due to temperature differences. We talked about that yesterday in the very beginning of the lab.
That's till the heat lamp heats the whole water up.
Until it heats the whole water up, but here's the problem. That heat lamp's heating over there, right? Is it heating over here as much?
No.
So where is some of the energy where is some of that energy going? Because we have a situation where the heat is being added over there, energy is being added over there, but not being added over here. some of that energy has to escape, right? Some of that energy is lost into the surroundings. Or in this case, if we're talking about the Earth, some energy is lost into space. So this process is just going to keep happening over and over and over again because of the fact that we don't have equal heating throughout the entire thing. Does that make sense, Tim? This right here, energy is higher over here. It is the amount of energy input over here is not equal to the amount of energy input over here. And so we're going to get a cycling that occurs in the matter because of that energy being unequal. Okay? Does that make sense? All right. Extension questions. Let's answer these together. Question number 1. Assume the bottom of the tank represents Earth's surface, meaning that all of the liquid throughout this tank would represent our atmosphere. So we're standing down here at the bottom. Everything above us would represent our atmosphere. In what direction does the fluid, air, flow near the polar region? If I'm standing over here in the polar region, in what way does that air flow?
The right.
Oh, it went to the right, back towards what? Towards the heat. What is the part of our planet that is heated? The tropical regions, the equator. So if I'm at the pole or somewhere in between, that air that is coming from the poles that's more dense is going to make its way from the poles all the way back to the equator to be reheated. It's going to rise through the atmosphere. It's going to slowly make its way back towards the poles. It's going to lose some of its energy over time. It's going to sink back down. And so we get this cycling from the poles at Earth's surface all the way back to the equator where it's reheated, it rises, and that process happens over and over and over again. All right?
So how does a convection oven work?
A convection oven is very similar. You get heating in one location. The heated air rises. It is cycled through the entire oven to only be reheated at another location. And that process happens over and over and over again. If you were to take a thermometer that was very, very sophisticated and very good at measuring temperature, you would notice that on one portion of your oven, the temperature is actually higher. And if you were to measure it over on the other side, it's lower. And so as you're adding energy on one side, it's cycling through the oven. I don't know if you want to try that because your oven gets so hot that you might not want to stick your hand in there and be like, oh, yep, it's colder over here and hotter over here. But that's really what's happening. Our rooms do the same thing. You guys all have houses that have a heating source. The area where that air, if you have like a forced air furnace, the area where the air is coming out, if you put a thermometer there, it's quite a bit warmer in that area. If you walk to the other side of the room, it's quite a bit cooler. That air that's coming out that's heated is going to rise throughout your room. It's going to make its way away from the area where it is being released, probably at the ceiling level. It's going to cool, it's going to sink back down, and it's going to cycle back through where it gets reheated by the air that's coming out of the floor, whether it's forced air or whether you have like radiant heat. Maybe you've got little radiators, like little thin things that are metal that run along a wall. The energy is going to be transferred into the air is going to rise, and that process is going to happen over and over and over again. Okay? That's how we heat rooms. One room is not going to be, or one portion of the room is not always the same temperature as the other side of the room. And that's typically why a furnace technician, when they put your thermostat in the house, they try to put that thermostat right in the middle of the house, knowing that the thermostat is going to read the temperature and then tell the furnace to kick on. If they were to take that thermostat and put it right up above where heat's coming out of a vent, that thermostat would always read that the temperature was quite a bit higher. Whereas you're walking around the house going, boy, my house feels really cold right now in the winter, because it's only turning on when the heat is being called for, when the temperature drops below whatever you set the thermostat at. So you set the thermostat at 70 degrees, it might be 70 degrees over on that wall, but the rest of the time you're spending over on this side of the house and you're like, my house is always cold.
I like how it is, since I was cold.
kind of like the basement's always cold, because most of the time with basements, here's the big reason for that. You might have vents in your basement that kick heat out, but what happens to heat? It goes higher. The air rises because it is less dense. And so in your basement, you're like, it's kind of cold down here. It's because all that heat, any heat that's being kicked out in your basement is finding an avenue to get up to the top floors of your house. Well, what do we do with roofs in order to keep that heat trapped? We insulate them. We try to find ways to keep that energy from transferring out of the house. So we insulate like crazy. That's why maybe if you have a second story bedroom, sometimes your house might be cold because your bedroom might be cold because it's not insulated really well. Some people complain about the fact that a second story house is always really hot. And the reason it's really hot is because all that air that's heating is rising to the top, and then if you got really good insulation, it's just trapped there. All right, did we answer everything for extension question number 1? What conclusions can you make about the relative air pressure at Earth's surface near the poles? All right, I don't think we answered that question. At the poles, if I'm standing at Earth's surface, I represent this little cat. I'm standing at Earth's surface. I'm standing down there. What is the air doing on top of me at the poles? What? At the pole, it rose up. What did it do over here? It sunk down. Mr. Torn, what's your thinking?
It's pushing down on you.
It's pushing down on you. Because that air's sinking, right? What is the air pressure going to feel like for me standing here then if all that air is sinking on top of me? High pressure or low pressure? High pressure. Because that air is sinking down on top of me, I'm going to have higher pressure on me. All right, now let's go over here. I'm standing over on this side. What was that air doing over here?
Heating up.
It was heating up and rising. And so therefore, what is the pressure going to look like around me because that air is rising above me? Higher or lower? I heard 2 answers. I heard higher and lower.
What was the question?
So if I'm standing right here,
Yeah,
and all that air is rising up and it's moving away from me,
low.
is the atmosphere putting pressure down on me?
No.
No. So is it high or low? It's low. The air pressure is lower because it's moving away from me. All right. Question number 2. Assume the bottom of the tank represents the Earth's surface. In what direction does the fluid or air flow near the tropics? Well, what conclusions can you make about the relative air pressure at the Earth's surface near the tropics? Where was it going again, Ms. Miles?
I have a question, so what are we putting down for 1 then?
Oh, let's go. Okay, well, let's go back to 1. It wants you just to talk about the direction near the polar region. What conclusions can you make about the relative air pressure at the Earth's surface near the poles? So number 1 is only talking about the poles. So if I'm standing over here at the poles and the air is sinking down on me, what are we saying the air pressure is over at the poles? Question number 1 is only related to poles.
Low.
If the air is sinking down on me,
Oh, high.
high pressure. So question number 1, what conclusions can you make about relative air pressure? Air pressure is high because the air is sinking down. And it wants to know in what direction does the air flow near the polar regions? Well, it's sinking down near the polar region. And I suppose at the polar region, you could probably make the argument that it's flowing back towards the equator if you wanted to say that. But at the polar region exactly, right here at this spot, that air was all sinking down. This fluid was all sinking down. And then question 2 wants to know basically the same thing, but over here, standing at the tropical regions. So question number 2 is same thing. What's going on over at the tropical region? So assume the bottom of the tank represents the Earth's surface. In what direction does the air flow near the tropics? In this case, we said it flowed upward, right?
What time do we get out of here?
We think that we leave
9:45.
at 10.
We leave at 45 because it's 10 extra minutes.
Yeah.
We,
But we started 10 minutes later. So we think that it might be 10 o'clock.
I have a schedule on my
So,
phone.
so 10,
It's
actually,
45.
9:55. So what we are gonna do is, we're gonna wait for Ms. Helminski to dismiss her students, and when we see them, we will know it's time to leave.
How do we know that they leave?
What's that?
9:50.
It's like a hallway.
9:50, okay. So the statement was
Only he can see.
that maybe we have about 10 more minutes.
Yeah.
I gotta adjust that clock up there, it still hasn't gone to daylight savings time. All right, are we prepared for question 3?
Yes.
Yes.
All right, question number 3. Air always flows from an area of greater density or higher pressure toward areas of lower density, low pressure. So high to low. Why did the air aloft flow in the opposite direction from that at the surface? Why did it flow in the opposite direction from the air that was moving at the surface? What do you think? Air, fluids always flow from an area of higher density to an area of lower density. Why did this liquid up here flow from here over this way?
Then a hot lot of energy.
That's probably part of it. It had a lot of energy, and so it's less dense. Ooh, it has to recycle. That's a great point, Wyatt. So the liquid that had a higher density, was moving across the bottom because it was more dense, right? But Wyatt said, well, it's kind of got to recycle itself. And so this liquid was kind of pushing everything that was over here back up because it was a little bit warmer. And so then this starts getting pushed back over just in order to make space or to account for the fact that space was made as that liquid was moving, right?
Mr.
If
Winter,
this liquid goes away, this liquid over here is going to push the other way. Did somebody just have a question online?
Oh my God.
yes, I did. Can I use the bathroom?
Oh my gosh.
I'm fairly confident you're okay with doing that.
Okay, thanks.
That sounds nothing like Eric.
It's because of his tongue.
Yeah, I didn't, that was a good question.
I thought it was easy.
I mean, I just appreciate the fact that he didn't decide to take his phone with him to the bathroom.
Yeah.
Oh.
Hopefully you would have needed it if you did.
Yeah. All right, question number 4. Are we doing okay over there, everyone?
Yeah.
Ooh, we're wanting to know what we should write for question 3.
Yeah.
Why did the air aloft flow in the opposite direction from that at the surface? It's because the air that moved out of the way created space for that air to move in. It created a void area. It sunk down and it moved. Well, something had to fill in that empty space where it moved from. So the air moved across the top because the cold, dense air that was sinking, it had to have space that was occupied by where it moved out of the way. So something had to fill that empty space where it moved from. Did I clarify? You're like, I'm still not sure exactly what to write.
So I kind of just put the air that moved and then I didn't know what else.
And then
Okay,
other
the
could-
dense air moved, making space for the less dense air to move in.
I wrote it created a void area.
Yeah, that's one way of saying it. Created a void area that had to be occupied by new liquid, right? New fluid. I'm fairly certain that this stool is not going to survive much longer. So at some point,
Maybe not.
when I go down,
Yeah.
I'm just waiting for it.
maybe call 911 if I am unresponsive.
You might have a.
Also, you only have to do chest compressions now.
I know how to do them, don't worry.
Good.
Alyssa's certified.
Don't need to
I'm
certify.
not watch out for your
Eric's
head when you fall. You
How is
can't
Eric
certify.
certified but you're not?
Because he's
Can't
no.
give me the lessons because,
She's too young.
no, I'm not. You just can't.
All right, because she's her mom.
Yeah.
Question number 4. If cold, dense air spreads out from regions of high pressure near the pole along the surface of the Earth and heads toward the lowest pressure near the equator. So it's spreading out, it's making its way back towards the equator, if that is occurring. Why don't we in the northern hemisphere continually receive our winds from the north? This is a leading question. It's getting into where we are going. Why is it, if we've got air sinking at the poles all the way up north of us, how come our wind doesn't always come from the north? Typically it comes out of kind of the southwest, right? Why is it that we have a situation where we are not constantly getting winds out of the north? Samar.
That convection thing?
Uh-huh. So the convection thing is definitely part of it. And so the question is, like we are somewhere halfway between the North Pole and the equator, aren't we? And so maybe we stand like right about in here somewhere, right? This is north. This is south of us. Why is it, okay, it could be, maybe even south of Florida near the equator. Why is it that where we stand, we don't always feel the wind coming from the north? How come the wind isn't always coming at us from that direction? Instead, it comes at us from somewhere over that direction. Somewhere from the west. Because that's predominantly where our winds come from, right? When we walk outside, most days, the wind is coming out of the west. Why aren't most days the wind coming directly out of the north? That's the question that's being asked. Mr. Evan? You seem to be distracted by something. Why don't you bring that something up here so it's not a distraction?
Maybe.
Oh, maybe wasn't the statement. It wasn't a question.
It's just like all the favorites I do at home, except those aren't favorites, are actually things I'm forced to do.
I know. That's how school works sometimes. We'll put it right here. You can pick it up at the end. There's lots of other things I'd love to do.
We get at 9:50 or 9:55?
9:55.
We think it's 9:50.
It's
not
just
me.
People are going out there right now.
Did Ms. Hominski's class leave?
I can eat a locker or something.
Okay, please be careful of the cords.
Put your.
Put your stools back up. If you could do me a favor and look on the floor, if you see garbage, could you pick that up? We will finish up question 4 when we return to it. Extension question? Yes, yep, we'll do all the extension questions, 1 through 8. Yep, so we'll finish 4, so we'll do 4 through 8 a little bit later today. Yep. See ya. All right, online folks. I will see all of you a little bit later today. Mr. Evan, you may pick that up. Mr. Evan.
What time? What time do we have to get back on?
Let me check the time, Eric. I think I know, but I just want to confirm.
Okay.
I got my sheet right here. So you guys are second hour, you guys will come back to me at 1:05 today. So 1:05 to 2:04, we will be back together.
Please come to the office. Manny Vickery, Elijah Powell, Brendan Brown, and Kennedy Friend. Manny Vickery, Brendan Brown, and Kennedy Friend. Please come to the office.